All right. Hello, everyone. Welcome. I hope you had a happy Thanksgiving. And welcome to Black Holes on Black Friday. Anyone go shopping today? No? That seems like kind of standard nowadays, right? So now, really, we own Black Friday, right? This is what you're here for on this day. um, so Black Holes on Black Friday, that's going to be our main topic. And we're going to get into um, where black holes come from, and that's going to take us all the way down the stellar evolution chain. And we'll have this demonstration up here for our black hole simulator. So I think we have a fun program in store. Before we get to that, though, I have a little introduction here. First thing, raise your hand if you're new to Kopernik, if you've never been here before. Oh, a whole bunch of you. Wow, that's awesome. Well, welcome. We're so happy to have our newcomers tonight, as well as our returning guests. So Kopernik Observatory and Science Center. It's part Science Center, which you're in right now. We have our different classrooms, theme classrooms. This is the Space Science Lab. We also have a Physics Lab, Earth Science Lab, and Computer Lab. And we welcome you to explore some of those different rooms at the end. I can even do another tour after the program if you want to see those classrooms and the tools we have. We also have some astro photos in the Computer Lab and down the long hallway. Those were all taken with our telescopes at Kopernik, and there's some images outdoors as well. If you haven't gotten to look through a telescope yet, we'll make sure you get that chance as long as the skies behave. And we have the moon and Saturn tonight are our primary targets, so lots to observe there. So a couple of things coming up. Let me get my mouse out from around the corner here. So we do have an event. The registration for this event does close tomorrow. So if you want to jump on this one, make sure you register by 11:59 p.m. Vigilia 2025, we do run this each year, and it's hosted by the Kopernik Society of Broome County. A little history there. Kopernik Society used to be the Polish Society of Broome County. So it's the same organization, but they switched the name to align with Kopernik Observatory, because they were the founders of Kopernik. And that's part of our mission, is to emphasize Polish cultural heritage. Because Nicholas Copernicus, or in Polish, Mikołaj Kopernik, was a mathematician and astronomer born in Poland. So we welcome you to celebrate the Polish tradition of Christmas at Vigilia. And that'll start, there's an open bar starting at 4 p.m. and at 5 p.m. the main festivities begin. And that's held at the Doubletree Hotel in Binghamton. So you can register online until 11:59 tomorrow. Or you can even speak with us after if you want to register here. There's some paper forms out front that we can set you up with. For our newcomers as well, one way that you can support Kopernik is through Kopernik membership. And there's some really nice benefits that come with our membership program. And among them is that you get access to over 385 science centers and museums across the country. And there's even some that are international as well. So if you go to this support page on our website, it'll take you through all of those benefits. There's, of course, perks for Kopernik itself, like getting admitted to Friday night programs for free, and discounts on classes and summer camps. So you can check out this page. Our membership rates are shifting. That's another point I want to emphasize while we still have a little bit of time left. To maintain our access to ASTC, our membership rates are going to increase for each level. So just keep that in mind. That starts January 1st, 2026. And it's also a great gift for the season. You can gift memberships too with our online form. So check that out. Other places to explore on our website, if you come way down to the bottom, there is a section with our clear sky chart. And this is an astronomical chart for the weather in our area. So it's the parts that are most interesting to us as astronomers. And among those, of course, the most important one is cloud cover. So the first two layers are different cloud cover models. And if you see here, that blue for tonight, that surprised me a little bit after some of the snowy weather we've had and the cloudy weather. So we have a good chance to see over the next couple hours some clearing. But the other two layers down here, transparency and seeing, those have to do with sky quality. Even if it's clear out, transparency and seeing play a role in how much of the atmosphere is turbulent. There's that affects our images in astronomy, and how much you're seeing through, because there's all sorts of particles that exist in our atmosphere. There's even a smoke map down here that we have to watch out for too. So blue across the board is ideal. That means super clear weather, but we'll at least take blue for cloud cover. All right, let's jump back. So our webpage is kopernik.org if you want to check those things out. We also have an active YouTube channel, which is just Kopernik Observatory. And in fact, we are, if I refresh this page, you will see we are live. We're streaming Black Holes on Black Friday tonight. So hello, Livestream. We try to present every Friday night program. If there's any copyright issues, we can't stream them, but we try to stream each one of these. So this season, we've had talks on National Weather Service, giving us a summer review and winter preview. We had our Astrofest programs, Fall Skies, Mysteries of Easter Island, the FNL, Power of Collaboration, all sorts of topics to explore there in STEM and beyond. So again, we don't just focus on astronomy, but tonight certainly is astronomy. And then if we go, other live programs that we do, if I scroll down to this one, don't worry, I'm not going to make you watch this one. It's 6 hours, almost 7 hours long. But this was the total lunar eclipse live that we streamed on Pi Day. And that was an early morning event. Over the course of 6 hours, we got to see the total eclipse. So you may not have caught it, because it was like, it was started at like just after midnight and then ended around 6 a.m. But we did do a time lapse of this. I can bring up here. So instead of watching 6 hours worth, we sped it up so you can watch the eclipse in a minute. So let's see the March 2025 eclipse. Now eclipses always start on a full moon, so they will only happen during the full moon, and it almost looks like during an eclipse it's going through the lunar phases, but it's not. Instead, what's happening here is it's entering the Earth's atmosphere, or sorry, shadow atmosphere. No, don't let that happen. The moon's entering the Earth's shadow, and when it does that and it enters the umbral shadow, it turns this beautiful red color. And that red color is coming from indirect sunlight passing through the Earth's atmosphere, there it is, and casting onto the moon. So one astronomer at NASA has a wonderful quote that it's as if every sunrise and sunset on Earth is happening on the moon all at once. Because what color are sunrises and sunsets? Yeah, reddish, right? Pink, red, orangey. That's where that color is coming from. All right. That was taken with one of our telescopes. Actually, that was with our little sea star, which is pretty amazing, which we will likely see tonight. Oh, that all I had to do there during the time-lapse building was adjust the exposure on the sea star telescope, and that was all I did. There was no filter use on that one. Yep. All right, so let's back out of this. I think I'll just do a full close. Yes? Oh, yes, thank you. That was a big one, too. Let's go back very quickly. If we go, actually, on the top, our year-end donation is up. Oh, there we go. So each year we run our annual campaign at the end of the year to support Kopernik's operations. And so yes, your individual contributions are critical to support our recurring annual operating expenses. And you can both donate online or just send us a check directly. This is really important because while we do get grant funding and stuff, it's not often for operations themselves. It's for infrastructure building and site building. So this is really important to support our future initiatives. All right, let's hop back here and start black holes on Black Friday. Maybe. This is the black hole. You like it? All right. So let's go full screen. And this is a lot of the pictures you'll see with black holes in this presentation are not real. There will be a couple that are, or at least based on real data. But a lot of the images are based on true simulations. So even this picture here, while it won't have this text going on it, this is akin to what you could expect if you were flying close to a black hole. And we'll certainly touch on that quite a bit. My name is Jenny Carty. I am the technology manager here at Kopernik Observatory, and I do a lot of education work as well, like tonight. All right, so one of the big topics that we'll focus on at the beginning is the life cycle of a star. So how stars form and the different parts of its life cycle. If we're to take it all the way back, we can start at a nebula. And there are some beautiful nebula out this time of year, especially as we head into the winter, like the Orion Nebula. And that's a great example of a star forming region. That's all a nebula is. It's where stars are born. You have these high concentrations and high densities of gas and dust. The gas in particular, your hydrogen, is the most important for star birth. So lots of hydrogen in a nebula, and when it squishes on down, it compresses and squeezes, that's where you get, like you see here, your dust clouds, and then this globule. And then finally, with all of that hydrogen contained in one place, it starts to collide. There's nowhere else for the hydrogen to go besides hit another hydrogen. Otherwise, they usually avoid each other. But all that can happen is, boom, hydrogen collides and a star ignites through this process of nuclear fusion. That's your protostar. So then we carry on through the stellar life cycle, and the coming slides are going to show us a lot of these features. So I'm not going to go too much further, but brown dwarf stars, main sequence, your red giants, white dwarfs, black dwarfs, and supernova, those are some of the features we'll see in the later stellar evolution. So here is a very cropped version of what's called the Eagle Nebula, sometimes known as the Pillars of Creation as well. That's usually what this narrow field is considered. And what you're seeing here are two examples of the same object, this Eagle Nebula. On the left side, you're seeing an image from the Hubble Space Telescope. And on the right side is one from the James Webb Space Telescope. So this is a much newer view. This is the Hubble view that's been out there for a couple decades now. One easy way to tell what's a non-James Webb image and what is. This doesn't work for Hubble because Hubble is based on more traditional optics. So you see how Hubble's stars have these 4 spikes? That will be pretty common amongst most telescopes. They'll have those 4 spikes. But on this one, can we count all the spikes? 1, 2, 3, 4, 5, 6, and there's a couple of smaller ones in between. So a total of 8. Only James Webb will really showcase that. So that's one way to tell. But notice how different these images are. This is a nebula. This is a star-forming nebula. All of these bright stars around it are funneling out from it after formation. you can almost see how there's like cavitation regions in the nebula, as if these stars have used up that fuel, right? Because it's pulling from the material in this nebula. So we're seeing some of that. All right. So here's an animation of what's going on inside these nebulas and how you get these areas of low density, not as many clouds, more diffuse, wispy clouds like you might see on Earth, right? And then some thicker clouds towards the center. These veins you're seeing here are where stars have enough. There's enough material there, and it's all close enough together that it ignites. And we get star formation. So the new stars can take on a variety of characteristics. You can have different sizes and colors. They can be blue to red, different surface temperatures, more mass is going to mean brighter and hotter, and more mass also means a shorter life. And we'll see that when we point out our diagram, how all these stars relate to each other. Now this is something, this is a picture that you can take home tonight if you like. I have this from NASA. This is an image of a protostar from the James Webb Space Telescope. And it has all the information to read on the back side here. So it's a beautiful lithograph. And let's talk about the image. It doesn't have a very clever name. It's, do I have it listed up here? No, I don't. So the name is L1527 IRS. And all that's coming from is a catalog number, because this star, taken by one of the best and largest telescopes out there, so it's seeing a very narrow part of the sky that even like our telescopes here at Kopernik and even elsewhere on Earth would struggle to see at this level of detail. So it's a very narrow piece of the sky, and that's why it doesn't get a fancy name, or at least not yet. This was the James Webb Space Telescope. Yep. So this is a protostar in action. It's this contraction of gas and dust. So all that nebula, that hydrogen comes together, squeezes down into that globule, and then the star ignites. But you still have a lot of material surrounding it. And all of this process brings it up to a temperature of 15 million degrees. That's how hot this gas is surrounding the star. And that's not uncommon, too, for the surrounding material to be energized that way. During a total solar eclipse, you see that beautiful corona around the moon from the sun. And that atmosphere of the sun is millions of degrees Fahrenheit, whereas the sun's surface is only 10,000 degrees Fahrenheit. So that really ramps up. It kind of just cooks the material around it. And let's see, some of these points I won't get into. Yeah, I think that's probably the most important point I'll emphasize here. So when this star forms, the outward pressure in the gas balances in the inward pull from the inward pull of the gravity. So that's, a star is this explosion that's being controlled by gravity. It's this careful balance at work. As we'll find, as stars come to the end of their life, the star's energy starts to win out against gravity trying to collapse it. And that's when stars grow and grow and grow and become things like red supergiants, leading us to eventually black holes. So it's this careful battle of energy and gravity. Oh, actually, one more thing I wanted to point out in that picture, one really important thing that you'll see in your poster too. Right at the center, this bright part is the protostar that will eventually just be its own solitary star. This gas will diffuse over time from the jets. But in front of it there, you see this kind of dark bar across it, right? That is the solar system forming around this star. Not our solar system, but someone else's someday. And it's this disk of material. We call it an accretion disk. A lot of things end up being disks in space. And that's where all the planets will pull from. There's no planets there yet, but over time, just like our solar system formed, this star will have its own solar system of planets. Oh, yes?
So why do we see like the, I don't know, like the polarity or the hourglass shape
Oh, like
material above and below?
the jets, yeah. And that's another feature so the question, I'm going to read it out to the live stream, so, because just one thing to know. Later on, we'll pass the mic around for Q&A at the end, but I'll read out questions for now. The question was, why are we seeing those jets in the protostar? And when this process of fusion is playing out, there is a lot of angular momentum involved. That's why you're getting this disk shape of material at the very near part of the star. And stars themselves end up being very magnetic objects in space. So this polarity you're seeing is most likely, I think I'd have to do a bit more research on it, but this is my best educated guess, is from the north and south pole of this star. So you have this magnetic balance playing out and these jets shooting off in opposing directions. And you see this same effect with objects like black holes, which are also heavily influenced by angular momentum. And you get these big jets shooting off into space. And I think we might see that too. Okay, we don't need any of this. So when is a star a star? So we're going to piece together this passover point from when you just have hydrogen, a cloud of hydrogen in space, to when you end up with a star. So we need nuclear fusion to take place to get our star. And that's when we have 4 hydrogens converting into helium in energy. So collision needs to happen. The hydrogen molecules, H2, need to collide to form helium and then energy. And this process takes out through E equals mc squared. That famous equation, right? E equals mc squared, where energy is related to mass. So you get net energy out when you get this collision of hydrogen. And it shows that while we can't create or destroy matter, energy is influenced there too. So because they are cross-connected, we can get net energy out from this reaction. Okay, yeah, that's good. So here's this process of fusion playing out. The collision of we don't have to worry about this. Just think of these 2 molecules over here as hydrogens colliding, and then once they combine, boom, you get energy out, you get a neutron flying out, and you get helium flying out. And this is what the sun is doing all the time. It's taking its hydrogen, and those hydrogen atoms are colliding at the very core of our star, and it forms helium. And through that process, you get a photon of light, you get that energy spitting out. And all of this big terminology here is hydrostatic balance. Hydrostatic equilibrium is the idea of the star's own gravity wanting to pull in, right? When you jump on Earth, Earth pulls you down. So the star has its own source of gravity because it's a massive object. But the star is also actively exploding. There's all this energy coming from it through this process of fusion. So you have this gas pressure from the plasma pushing outwards. And the star is stable when this is in hydrostatic balance, when it's equal. And here is the famous HR diagram. HR stands for Hertzsprung-Russell. And on the bottom here, you see a temperature gradient. And on the left-hand side is about luminosity, so how bright the object is. Now, some of this is going to be a little counterintuitive. On the bottom of this, you have dimmer stars, and on the top you have brighter stars. So that's fine. But on this scale you have hotter, and on this side you have cooler. Okay? And that seems a little weird, doesn't it? Because what do we notice about the colors? If this side's hotter, or sorry, cooler, I'm gonna mess you up. If this side's cooler and this side's hotter, what's weird about the colors on display there? Yeah. Yeah, that's really weird, right? When you walk up to a faucet, a sink, and you look at your different sides, right? You have left is red and hot, right is blue and cold. That's counter to what we're seeing up here. But this is how when stars burn, and they burn hot and they burn bright, they are blue. And when stars burn cooler, they are red. And then there's the in the middle, in between, where you even get some white color, you get yellow and orange, and so on. So this is just the nature of physics. It's this whole thing about black body radiation. The most simple example is if you think of an old fashioned light bulb, which some of you, especially the younger ones, probably haven't seen, an incandescent light bulb. If you start at a low energy, it's red or reddish. As you crank it up to a higher energy, it starts to turn white. And if you crank it up too high and push too much energy through it, it will pop. But just before that pop, it's very blue in color. So it's just this nature of radiation, how radiation behaves in a vacuum. All right. So here's where we can break this diagram up into different types of stars. So we have white dwarfs down here, supergiants, both blue and red. So a red supergiant, as an example, is a star like Betelgeuse, which we'll see tonight in the constellation Orion. And then you go down in scale. So you're getting some, ultimately, as the star gets smaller, it's usually going to be dimmer. And there's less material there for it to burn. And then, yeah, up in here, you have your bluest and brightest stars on the left-hand side. And of course, those are the hottest. Those also don't burn for very long. They are very, I guess you could say, they're very speedy with their ability to burn the hydrogen and then eventually burning helium, and they give us the higher elements that we see in the universe today. And that's good because they don't have long lifespans. They'll burn out quick, but they'll give us higher elements that we need for here on Earth, and we use them as resources. Okay, so looking into a star now, layers of the sun. We have a core that's 15 million degrees Kelvin, not degrees Fahrenheit. With stars, we're going to measure in this metric called Kelvin. But either way, really hot. That's all you need to know. Radiative zone. This is where the actual fusion happens. And then out here, you start to have the energy from that process of fusion radiating outwards. And then we have a convection zone. Similar to Earth, we have our convection layer in our mantle, and that's what gives us our magnetic field. Similar with the sun. When you have this motion of plasma, you get this magnetic field. So the sun has a very powerful magnetic field. And then the surface of the sun is going to be called the photosphere. And you see we're going down in temperature as we get outwards from the core. But then once we pass this line into the atmosphere of the sun, it starts to crank back up. So the corona, as I mentioned earlier, you're pushing outwards to millions of degrees Fahrenheit. What's amazing about this, though, you have this energy forming here. How long do you think it takes for a particle of light, for light from where it's being formed to get out to the surface of the sun? Any guesses? Any thoughts? What do we think? I don't, any guess is fine. Any guess? Let's just hear some ideas. Yes. 3 minutes? All right. Any other ideas? Yeah. 5 million years? All right. We got the extremes. That's awesome. Any other ideas? Yes. 4 minutes? All right. So this is, I like that we went right for the extremes. That's perfect. And what's amazing, we're talking about the center, the core of the sun, out to the surface of the sun. It takes about on average, 10,000 years for energy from the core to get out to the surface. That's no time at all for the sun. The sun's been around for 5 billion years. So that's like, a few seconds compared to how we exist. But yeah, pretty amazing that it takes that long for that energy to get out. And then once it leaves, it's free to go. It's radiating out, and from the sun's location to where we are, it takes about 8 minutes for that light to get to us at light speed. So it shows you how dense a star is too, because that's the reason it has that energy has trouble leaving. It has to get through all of this matter that's in its way. All right. So here's a nice little scale comparison to what we're talking about. When on that HR diagram, it really wasn't selling just how big the supergiants are. So here's Earth. Can you see it? Yeah, a little speck of dust. Here's our sun. You can fit about 100 Earths across the sun. So 100 Earths in diameter. And then you have a red giant. This is probably about the size of Betelgeuse. Again, that star in Orion. And we can't even see the entire thing. You're talking about something that's hundreds and hundreds of times larger across than our sun. That's incredible. All right, so we have these big massive objects, these stars. And because they're so massive, they warp space-time. This is our modern understanding of what gravity is. And a star is really bending this fabric. And we'll see this later with our simulator. We literally have some fabric out here. So if you consider this flat piece of fabric here, your space-time, let me get this corner too, right? Really thin. When you put something down into it that's super massive, like a star, it pushes right into it and bends it. It curves it down and creates this funnel. We model it as a funnel shape. And this is why things like planets around a star go around it. They spin around the sun, and they're following this curvature that the star is making. And it's not just planets that are reacting to stars. You also have stars reacting to stars. And that's what makes up an entire galaxy. As we'll see later, there's even, with galaxy formation, there's even black holes involved with that are bending space-time. So this is really important because when you have a black hole, you're talking, at least mathematically, of something that's of almost infinite, basically infinite mass. And the role that plays on space-time curvature is really astounding, especially when you travel into a black hole. That brings up some interesting questions. Now, what's also amazing about this is the strength of gravity from stars is so strong that light reacts to the space-time curve. And so if you have a star out here in space, located here, and you're looking from Earth, now to us, if we were just to take this as an image, disregard this section here, that star should be blocked out by the sun from our perspective. Sorry, space shuttle. From our perspective. But because the star's light comes down this way near the sun, it shines, and hits that curvature of space-time, it gets bent. Gravity bends that star towards us so that we can see it. And this was a big moment for science when this was proved, because basically this concept proves Einstein's theory of relativity. And how did they do that? How are you going to see a star around the sun when the sun's so bright? That's a huge challenge. A solar eclipse. So, during a 1919 solar eclipse, this theory of relativity and space-time curvature was proven experimentally with a telescope, because this is a moment when you can use telescope equipment and gear to safely observe around the sun. This is the moon here blocking out the sun, and the cloudiness around it is that really high temperature corona. That's millions of degrees. And it gets dark enough during a solar eclipse that we can see stars. And because we have a really good model of the sky, the stars that were showing up there were not a direct flight from our viewpoint. Those are stars that really should be behind this, but their light is being bent around because of that bending of space from the star's massive gravity. So already you're seeing the stars themselves are massive objects. And we're basically visited this part of the plot in our stellar life cycle, from star birth to what goes on during a star's main part of the life cycle that can last from millions of years for blue stars, and billions of years for cooler stars, like our sun, burning for 5 billion years, expected to burn for about 5 billion more. So let's dig a little deeper into this, because now we're going to focus on what happens when a star reaches the end of its life. So the next phase, for stars that are usually main sequence, like our sun, they often will become planetary nebula structures. Now, from what I understand, our sun is going to be pretty clean when it expands out, and it likely won't leave behind this planetary nebula due to its star type. But a lot of stars on that main sequence, they're not very massive, they're middle ground, and they will end up expanding at the end of their life cycle, and as that is diffused out, that gas gets spread out, you get these clouds around the dying star. So they often look like rings. The reason they look like rings, though, if we think of this in 3D, it's this sphere, right? A star is a sphere. And as it grows and grows and grows, it's leaving behind this larger sphere of cloud. And when we look at it in space, we're looking into that cloud, and the thickest part of it is going to be on the sides. Think of cutting a cross-section of a sphere, cutting it in half. You'll see a ring. That's basically what we're seeing. So this is a very sphere-like cloud, but we're seeing the thickest parts of it from our perspective. And then this is the dying star at the center. So that is a white dwarf star. Very dense, but over time, it's just going to burn and cool off. And that will be the end of that star's life. And we do see these in the sky, like the Ring Nebula is a good example. We could see that tonight, setting in the western sky. Dumbbell Nebula as well. There's lots of these out there. Yes?
So are we looking at the scale of the pre-existing star, or is that the scale of the solar system?
This is probably, these planetary nebulas are reaching to the far extent of the solar system. That main cutoff for a solar system like ours, for example, is still being debated. So Like where do we consider our space, like in the solar system space, and then interstellar space? Where's that line? But that's what we're really looking at here. We're not. This might actually be another star, but it could be in the background. That's my best guess. But yeah, this is more to the extent of where this star solar system was. So akin to our Kuiper belt. Our Kuiper belt is way, way out there. And even the Oort cloud, you could think of that too. All right. So here's some other images of planetary nebula. They take on all sorts of different shapes and sizes, but the fundamentals of them are the same. You have a star that's grown, and is leaving behind a white dwarf at the center with a stellar cloud around it. And this cloud is filled with higher elements too, because over time the star is burned and burned and burned. So you'll find things like all these colors are coming from oxygens and helium being ionized. All right. Let's see. How should I want to go through this? Well, I guess this is just explaining what I've gone over for the most part, but we have the core of a star is all that remains after the planetary nebula spreads out. It's very hot, and it's about the size of Earth, these stars. And that's our white dwarf, and they form if a star has less than 8 solar masses. So a star 8 times the size of our sun and less, so that includes our sun, would potentially become a planetary nebula. Not always, as I mentioned, the current astronomers, they don't think that our sun will necessarily become as a beautiful planetary nebula like we see in the skies. But 8 solar masses and less, that's what you'll get. So that's a white dwarf. But another offshoot is where we can have our supernovae. And when you're 8 solar masses and beyond, that's where you have the chance to form a black hole. So a star will explode in space through among the largest explosions out there in the universe. And this supernova, when it happens, the star rapidly beats out gravity in almost an instant. And when that happens, it's a burst of light and energy. We can actually see a sample of a supernova in the down the hallway. We have a picture of I can't remember if it's Pinwheel or Triangulum now, but one of the galaxies, and we see a supernova in that galaxy, and it's already faded away. You couldn't see that right now. They're pretty instantaneous relative to space-time. But our black holes, during the collapsing phase of a supernova, that's where you, instead of a white dwarf, or you also saw a black dwarf there, which is just the cooler end of that spectrum, you end up with a supermassive object after a supernova, an object of almost infinite mass. And this intense gravitational field is left when this giant star collapses. It's much larger than the sun, and gravity becomes so big that it compresses, forming a black hole. And this is the effect that we get. Again, this is just a simulation view. It's not a real picture. But a black hole is called a black hole because it is the absence of light. Light can't escape black holes, so when you look at one, it's going to be very dark. Now, the surrounding material is energized, and it's not fallen in yet. But as soon as it crosses what's called the event horizon, boom, it disappears. And this crossover point is right in here. And light can't escape. Nothing can escape once you cross that event horizon. So if we look at this mathematically, we go back to our example of space-time curvature. We have, they call this a singularity. This point that just stretches way down. This is your infinite mass. So it's this funnel, and once you cross over this event horizon, right here, boom, you're stuck, and you can't escape. So if a black hole is near a star, don't worry, there's no black holes near us that are going to be doing this. Black holes, evidence for black holes becomes pretty apparent because of the way they affect things around them. So we really don't have much to worry about because we're not seeing any weird perturbations in our solar system or a little beyond. That would be evidence for a black hole. And you can see the way it would start pulling this material into this disk. We saw a more zoomed in version of this picture before. And over time, that material will be pulled down into this gravity well and be sucked down. But as I always mention, as I know, Sasha, you know too, our professor at Broome always emphasized that black holes are not cosmic space vacuums. And I love that framing because you can orbit a black hole. It's just a source of gravity. It's an intense source of gravity, but as long as you don't get too close, you're not going to be sucked in. And there's a very clear point where that plays out. You definitely, if you can avoid it, don't get close to a black hole. But just to say that black holes probably play a larger role in our universe for how it behaves and interacts than any sort of destruction that plays out. So keep that in mind as we explore these. So you can orbit a black hole, and you can do so safely. Get too close, then you have a problem. What was I thinking? Okay, yeah. So how we first started to discover black holes out there in space. We can't see them because they're absent of light. Light's being sucked in, so how do you detect one? Well, you have to look for other evidence, and among those are the type of radiation that's surrounding and jetting out from black holes. And this is higher radiation like X-rays and gamma rays. So those are the type of light that you want to look for. So something like the Chandra telescope, which we have it pictured over on that panel in the room, studies space in X-ray. So something like the Hubble Space Telescope, or even James Webb for that matter, they're not looking for this type of light. But we can use certain instruments to do so. All right, yeah, this is a good diagram. So as mass increases, so does the gravitational pull. So if you're trying to throw something up into the air on Earth, you're never going to be able to throw it hard and fast enough for it to escape. But theoretically, you could. And that's what we do with rockets all the time. When we launch astronauts up into space, we get them going high and fast enough that they are able to just keep skipping over Earth's gravity and into an infinite loop around the Earth. So they're just in constant free fall as they speed around the planets. And then if you go even faster, you can escape Earth's gravity, which takes a lot of energy. So that's why we haven't quite sent humans to Mars yet, for example. We need the right equipment to do so. But we have sent other spacecraft and robots out there. So you just need enough energy to do it. Some big rockets. But light has no problem leaving Earth. You shine a big, bright flashlight into space, that light will keep spreading out, spreading and spreading. Light's very fast. So signals that we've sent from Earth, radio signals, all the sorts of stuff, that's spread way, way out into our corner of the galaxy. But light around a black hole, now it can't escape. It's not moving fast enough. The fastest thing in the universe can't move fast enough to escape the gravity of a black hole. So this is where you get that bending of light too. So it will react to large, massive gravity sources. And with a black hole, it's all just going to fall right in. It can't escape. So what's amazing here is in galaxies, you have a black hole. This is a illustration of the Milky Way galaxy. We don't have a real image of the Milky Way because we can't leave it with our current technology. So all we can do is piece it together. So this is an artist's interpretation based on data of what the Milky Way could look like. And it is a spiral galaxy. We know that. And we know there are other spiral galaxies out there, like Andromeda, for example, is our neighbor spiral. And we've studied galaxies closely and their cores closely enough to know what's going on in here. And when we see it, I might have this slide. I do. I think this is an animation, or I thought it was. Maybe not. Okay, I guess that animation's not working. But when we look at the center of galaxies and study the stars around them, they all end up orbiting a central point of mass. And that central point of mass is a black hole. So at every center of a spiral galaxy, you will have a supermassive black hole, which is interesting, right? Like, that brings us back to the idea that they're not space vacuums. In fact, they're probably very important for galactic formation. Here's the Pinwheel galaxy over here. And again, right at the center, it gets nice and bright. And that's because there's so much stars clustered together around that central point of mass, the black hole. So here's that X-ray evidence for all that energy at the center of our black hole, which is called Sagittarius A. This is the black hole at the center of the Milky Way galaxy. This is how we studied it before, and this is how we're starting to study black holes. Over the last few years, a new telescope network was created, several years now actually, called the Event Horizon Telescope. An Event Horizon Telescope is made up of systems across the globe, effectively turning Earth into one big telescope. And that's the only way we'll ever be able to collect enough data to piece together images of a black hole, like this one. I believe this one was from, oh, I forgot what galaxy. Sasha, do you remember what galaxy this one was from? I can't remember. I guess I don't have it in my notes. It was that first black hole image. Because they went for an easy target first. Something that was face on like this. Because when you're viewing a galaxy face on, you're looking through less material. So they took an easy target first, so they wouldn't have to fight against all sorts of other stars and things in its way. Oh, okay, M87 was the galaxy. And that made it easier to piece together this data. Now, it's not like the Earth is one big telescope. It's little, or, well, decent-sized telescopes around the Earth. And if you think about, how can I frame this, I guess? Like, our telescopes at Kopernik, like our 20-inch, is a big mirror. It's like this big. If you took bites out of that mirror, the telescope would still work. You'd just be missing some data. So your image of Saturn, your image of Jupiter or the moon or anything would look fuzzier, it wouldn't look as detailed, but you'd still have data to work with. That's like what the telescopes are on Earth for this event horizon. It's bites out of this network to get us enough data to piece together an image. So this is the one from N87. This is our black hole at the center of our galaxy, Sagittarius A. So compared to the views we saw earlier of black holes, let's get out of this for a second. like this one, we see how there's this ring of light around it. This is about what our simulations expected to find with these two images from M87 and from our galaxy. You see a ring of material. You even start to see some evidence for an accretion disk around it, which you often see with black holes. Let's go down here. This takes a minute. Oh, one day maybe. There we go. So, again, piecing together what we're seeing in that image. We have our supermassive black hole. We have this disk of material that's swirling around it, funneling through that space-time curve. And then, if we kind of look at what the Event Horizon telescopes are seeing, it's showing you what this looks like. So you have your Event Horizon crossover. This dotted line is marking that out. That's where light's not escaping. And surrounding it, you have that disk of material. So this is showing you what we're really seeing from our black hole. We're looking down at its pole when we get these images. All right. And that makes sense for M87. For Sagittarius A, we wouldn't see that. We do see that accretion disk because we're looking through the disk of our galaxy. All right. So what is it like to go into a black hole? This is just our thought experiment. We're not going to demonstrate that for you today. But we have Einstein saying gravity bends space-time. Once you pass the event horizon, there's no going back. You get stretched and stretched and stretched and stretched and stretched. And we call that process spaghettification. You want to be spaghetti? If you go into a black hole, you become spaghetti. Stretch, 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 stretch. And eventually, as that process plays out, you get really ripped into atoms. It gets pretty crazy if you're in a black hole for long enough. So, and then you just funnel down into that crazy, infinite. It's kind of scary as I say it, but again, no black holes near us, so it's more just fun to think about. Keep that in mind. So a myth, black holes will spit you out the other side of the universe. Fact, no, there's no getting out once you're in. So the idea that black holes are these portals, there is a mathematical concept called wormholes that could be theoretical points that would connect space on different sides of the universe. Black holes don't do that. Black holes are, boom, infinite voids. But then again, it's also the science that is, a lot of it is based on mathematics. So the math tells us that's what happens. You fall in, you don't get back out. The only way to know for sure, I guess, so you gotta go jump in. But then you can't send a signal out, so we still wouldn't know. All right. I don't know if I want to get into this. Let's actually go to this video first. And we have a demonstration to do. So this is a simulation of what happens when you fall in a black hole from NASA. So you see that disk of material spinning around it as it funnels down. And now we're flying above it, and you see this is really important effect. At first, this video does a good job of it. You see on this side the disk of material that's facing you. This part, this ring that's forming, is that same disk of material, but the gravity is so strong, it's bending the light from that material up and around the black hole. So when we pass overhead, you really get a sense of how that's working. So flying over the north pole of this black hole, and then falling into it. And as we fall into it, it's going to show you how all of that gravity is bending the light around you. So these aren't really optical effects in their traditional form. They're gravitational optical effects. Gravity is so strong, it's bending the light. And as you cross over into the event horizon, things do just get dark. So this is a 360 video, by the way, if you have a VR headset at home. It's a fun one to try. That's part of the reason why it looks so warped to some degree, but it is a fun VR video. So this is showing you where you are with respect to that event horizon in the center. But once you cross over into that event horizon, everything goes dark. You won't see any light, because light can't escape. You can't escape. Everything's stuck inside. So you're stuck with the light around you. That's what you get to see as you stretch and stretch. Alright. Now we're going to model this. And then we'll do a little Q&A before wrapping up. So we're going to model this up here, and I would love a couple of volunteers. Anyone want to volunteer? Okay. See one hand up there, and there. Yep, come on up. You want to come up too? Sure. All right. So we'll just stand around our black hole simulator. You can spread out a little bit. Any other volunteers? We have a couple more spots if you want to. Yeah, you can come. I see a hand raised there. Come on up. All right. And this will be set up afterwards, so if you want to explore after the fact, we can do that too. So let's bring up our model of a black hole here. This idea of bending space-time. And what we're going to do, this is this flat surface that's spreading across. There's nothing in space right now. No stars, no black holes. But we're going to send one in. This is a very heavy object. And if we put it right in the center, it bends space just like this. Now we have a funnel going right into the center. So, what we're going to do, don't do anything with the marble yet once I hand you one, okay? Just hold on to it for now. Let's give each of you a marble. There you go. Perfect. And what I want you to do first, don't let go of it, but put your marble right here, right in front of you. Perfect. And then just let go. Yeah, everyone let go. Perfect. And what happened? What'd you see? It just went right down, right? So our marble didn't start with any speed. And so when we just release it, the only place for it to go is to follow a path. Oh, look, it made its own little gravity well. There you go. So the only place for it to go is to follow the path of space. And that path brings it right to the black hole. Now what we need to do, we need to give our, we can call these little planets, we need to give our planet some speed. So again, don't do anything yet. Give each of you a new marble again. So now, we'll put it right out in front of us once again. But you are going to push your marble to the right and release. Give it some speed to the right. Okay? So throw it to the right. Try that. Ooh, now what are they doing? Yeah, they're circling around it like the planets do, like the stars can do. They're circling around that center of gravity. So your little planets just now were orbiting around our black hole, right? Now, eventually they did fall in, which I told you that wouldn't necessarily happen, right? We can try again. This is science, so we gotta experiment, go through multiple experiments. So maybe try, I don't know, give it a little more speed, and moving in a little different direction. See what happens. Ooh, one reached escape velocity. Maybe one over here too. Yep, 2 reached escape velocity. So a couple of them moved so fast that they were able to escape this gravity well. And, oh, those ones are going for a long time. Those were good throws. So they were able to escape. You got enough speed, just like launching a rocket ship off of Earth and going to Mars, you reach escape velocity. So you can put a lot of energy into your planet and make that happen. But the first time, we didn't have quite enough energy. And it just eventually fell in after orbiting around that well. Now, what do you notice too? As it gets closer to the center, what do you notice about its speed? Yeah. It increases, yeah. So as you get closer to the center of this object, of a black hole, the speed of your planet that's orbiting will increase. And that's just like the inner planets of our solar system, right? We're moving pretty quickly around the sun once every 365 days. But Mercury, even closer to the sun, is moving super fast. And that's something like 60, 80 days, something like that. So let's try again. And notice too, when we have multiple planets in action, we got some collisions as well, right?
If they were the same mass, they would probably just completely crush.
Yeah, not something we want to experience probably with our planets colliding. So yeah, try again. Give it another throw, see what they do. Ooh, there's an escape velocity. You want to try again? Ooh, yeah. Some nice patterns forming too as planets go in and out in between their orbits. But things do get really chaotic as they go to the center. Now, yeah, as I said, they wouldn't necessarily fall in. If they're in orbit, if they're orbiting way out here, it takes a while on Earth here with our model. But in real space, if we started a planet out here from the black hole, pretty ways away, it should just keep on orbiting. Keep on going round and round and round forever. The reason why we can't model that in here is because we have friction. We have the friction, like if you feel this, this is like a spandex material, it's rough, right? It's not perfectly smooth. There's some roughness to it.
Why doesn't the other planets just go in if they're far away enough?
Well, oh, if they're
Just go in.
if they're far enough away.
Yeah, but like, why didn't they get in? If they catch me on a gravitational field, why don't they get in?
Yeah, like what we're describing here, I guess, is that when they are far enough away, they won't be pulled in, just like Earth won't be pulled into the sun. The sun is a well like this. It creates a well in our solar system, but because we're always moving at the same speed, um, we just stay in our orbital path around the sun. Same thing here. On Earth, we have friction that's slowing our objects down, both friction of the material here and friction in the air. So the air in the room will slow things down, just like a space shuttle coming back to Earth. It'll slow that down. So that's what we have to work with on Earth is friction. But in real space, there's nothing for those objects to run into. So they just keep going and staying in orbit around the object. All right, we'll wrap up with just giving you each a couple of them. And let's see what real chaos looks like.
What about the ping pong balls?
Well, we could try those too. I can give you each one of those as well. Yep. We'll give you 2 marbles and 1 ping pong ball. There you go. All right, let's see what happens. Oh, you need one too, sorry. My bad. All right, let's see. Let's get some collisions. Oh, we lasted a while there without any collisions, but now they're really going. And you see when 2 collide, that really slows them down, right? So they just kind of fall in. Didn't take long. Once they all got close to the center, everything started collapsing. Whew. Yeah, there's some extra.
That might have been from one of the first skin collapsing ones and we just never found it.
That may have been. Yes, I think you're right. It thought it was safe, I guess, but nope. Into the black hole you go. All right, thank you so much for your help, everyone. You can go back to your seat. Wonderful. All right, and to wrap up, I'm happy to take any questions, but I will bring the mic out to you so those on the live stream can hear the question first. Do we have any questions from the audience about black holes? Yes. Here, I'll give you this quick. Yeah.
Okay, I have 2 questions about black holes. One, does fusion still happen inside the black hole?
Mm-hmm.
And 2, like we're always talking about the event horizon as this absolute thing, rather than, how do we know like the event horizon is this absolute horizon rather than an equilibrium of light that may be coming from the inside of the black hole and the force of gravity that's balancing that?
Yeah.
How do we know that's like a solid thing?
Well, let's look at one of the pictures again. Maybe look at the real world image. Yeah, let's do that. I guess where we're really considering the main event horizon is where we stop seeing light. So my best guess is that's where that point is, which is where light is not escaping. But I suppose like there could be some consideration like that it is more of a gradient, because if we look at the funnel itself, the simulation of a black hole, arguably the event horizon, I kind of think of those, what are they called? There's a plant, a carnivorous plant that bugs fall into. Do you know the name of it? No? Oh, pitcher plant. Yes, that's the one. Venus flytrap is another one too, but pitcher plant is what I was thinking of. And they have a very similar shape, where you cross over this point and then you fall in and you can't get out. So there's a little subtlety here, maybe to the event horizon, but it is a pretty, if you were to look down this, it is a pretty strict cutoff, in my mind at least. I don't know if that really answers your question, but yeah.
Well, I guess my first question, like, is there fusion happening?
Oh, that was the other
at
one
the
too.
center?
Yes.
Like, okay, if there is still fusion happening at the center of a black hole, like, what's the difference between like a core of a black hole that's producing high energy light or low energy light, and right, that's going to affect where the event horizon is, in a way, maybe.
That could be true. My understanding of the physics is limited, I think, with that in that regard. But yeah, I'd have to do more research myself to understand that. But as far as like fusion, that's a really interesting question. Is like if and things can still happen once you're inside. I think there is that element of decay that plays out. Like down at the atomic level, particles are being stripped. So even hydrogen being the simplest particle out there, you're having that being pulled. So H2 becomes just your hydrogen atoms, and then you don't likely have much going on at that point. But I don't know. It's interesting. Like you hear all the theories too of like, okay, well, what if you have all these universes forming inside a black hole? It takes us down another road. It's like, ooh, crazy. Yeah, fascinating idea. I'd like to learn more. Thank you. Oh, yes. Any other questions? Sasha, do we have any questions from the live stream?
Yeah, just one.
Okay.
Linus asks, wouldn't you be ripped apart before you see the light go away? But it just into the
So the question on the live stream was, wouldn't you be ripped apart before you see the light go away? Yeah. That spaghettification process, it sounds fun, maybe to be spaghettified, but yeah, you'd really be having a bad day. So, any other? Oh, yes. There you go.
What it sounds like the black hole is not really a hole. It's just something in the middle of space with a tremendous amount of like force pulling things towards it, as we call it gravity. So my point is that really a hole, or just something in there as like a center of certain like a galaxy universe for the whole system to just circle around it? So when we think about a black hole, people talk about everything falls into it. But in reality, they don't really fall into it. It just kind of forms the system to spin.
Yeah, like there, from what I understand of it, there is this play of like what's happening mathematically and what's happening physically, and so like yeah, maybe you're not like infinitely falling down into this pit, but yeah, like as to what's going on inside, I think that's just such a new and modern area of physics that's still being explored. So. Yeah, I don't have all the answers for that side of it, but I love talking about it. It's fascinating.
And the second question is like, when we're talking about like matters orbiting the black hole. I mean, they have the energy, they have their speed and mass to be able to sustain the gravity of it.
Yeah.
But in science part, where are those matters getting their energy from to be like that?
That's a good question too. I'm not sure. That's a lot of this will be. I'm not an expert, by the way, on black holes by any means, but like I can speak to the initial science of them for sure. But my knowledge is limited here. But really good questions. Yeah. Go.
So, what makes the black hole have so much? Like, what makes the black hole have so much gravity?
What makes it have so much gravity? So when this collapse of matter, let's go back to the stellar evolution chart. It's a wonderful question. So when a star goes supernova, there is the explosion effect, but the matter isn't just leaving that central point. All the energy and matter associated with the star too is collapsing down at that center. Similar to what you have at the center, the remnants from your red giants, like our star will be one day. Yeah, you have these outer layers expanding out, but you're leaving behind this very dense matter from the star's core. That's the same effect with this supernova. Once we get from a red supergiant, yes, you'll have some outer layers booming and exploding out into space with all that energy. But then you also have this secondary phenomenon where every thing closer to the core in the center is collapsing. And all that energy and matter is collapsing to such a dense and small object that things start getting pulled down into that space-time curvature. So that's a really good question. You just have so much matter and such high density that the collapse of that creates that singularity event. Yes. Oh
And
yeah.
also-
We can.
And also, why does like, but also if all the gas from the star gets sucked away, will it just explode?
If the gas gets sucked away, wouldn't it explode? You mean during a supernova?
Like if all the gas just goes away, will it just explode?
No, like, are you thinking like the gas forming into another star, or? I guess I'm a little confused by the question.
Like if all the gas just gets, if all the gas just goes away and it's just and it's just like the star, will it just explode?
Not necessarily. Like if we're focusing on the supernova here, that gas gets spread out, and those outer layers for sure aren't going to be doing much. But it's that action that happens closer to the core, where everything's getting close together, that plays out in the supernova and why it ends up being so high energy and so bright. We can show you that picture down the hallway too to check that out. But hopefully that answers it a little bit. So yeah, I'll come back for that. And one more here.
So this is just a question because I think it would maybe help think about how black holes form as well. But my understanding would be the black hole starts as a supermassive star with an amount of mass and amount of gravity. And as it collapses, it becomes more dense, but the gravity should be relatively the same.
It's the collapse into a single point. I don't think that was an old mathematical
But the gravity
model.
around the total gravity, the total mass of the object
Yeah, it's
remains similar, or maybe even less after going supernova.
yeah, it's like this picture here. I do think does a good job of describing what's happening. Like, you have something that is much, much smaller than the object it once was. So all that matter is just being collapsed down to a hyper-dense object. And when that happens, you have space-time getting pulled down at that more singular point. Versus when it was a more spread out, it may have been a supermassive star, so still pretty deep, deep gravitational well. But now it's being pulled down to a more central point. That's kind of how I think of it, at least. But yes, you're right. Like, that mass and everything is not going to come from nowhere. So it is sharing similar mass to that star's core at the time. Oh, we got a couple here. Yeah, you can pass it.
So how do you make a black hole?
Oh, you want to make one right now? This is the best we can do here as far as a model goes. But making a black hole requires these big, big stars, like we saw. Well, even bigger than this one here, because this is being classified as a red giant. A red supergiant is even bigger than this one. And that's the only way to do it, is to have a huge, big star that reaches the end of its life.
So they use gravity.
Yes, gravity is the big thing there, yep. But gravity and a big explosion.
What kind of gas do they use to make a black hole?
What kind of gas? So what exists surrounding a black hole is going to be what the star was mostly made up of.
Hydrogen gas?
Hydrogen, yeah. Yeah, so you'll find some hydrogen. I mean, and then some helium too. The star is, most of the time when the star reaches the end of its life cycle, it's burnt through its hydrogen supply and it's moved on to the next levels, like helium. So yeah, you'll find those gases in it, yep.
what's the biggest supergiant we know?
I think it's among the biggest, at least, is a star called VY Canis Majoris, and it's a massive star. I should have had this video in here, but there's a beautiful video of star scale and all the different stars out there and how they compare to each other. There's a couple versions on YouTube, but that'd be something to explore. Because when we talk about how big these stars are, they're so big we can't even understand it. Like, we can't comprehend it. Our star alone is so big we can't really. 100 Earths across. I've only been on one Earth. How would I know what 100 Earths looks like? So it really gets vast beyond our human scale. But yeah, that's the biggest one if you want to look that one up. VY Canis Majoris. Oh, we got some more questions back here. Oh, good. Very inquisitive. Awesome. Of course.
How long do stars actually live?
Oh, how long? It ranges. So if we go back to our chart, if we go back to this chart, this is our HR diagram. It ranges quite a bit. So your bluer stars don't last as long. They can burn out they use more energy. They burn through their energy quicker. So they burn through their hydrogen and their helium quicker. And that's why they burn so bright. They're burning bright because they're going through their fuel supply faster. And these can only sometimes last, a couple million years, and then they're done. And then these ones over here, your redder stars, like our sun on the main sequence, eventually becomes a big giant star. And yeah, a red giant. And that process takes 10 billion years. And we've gone through 5 billion so far. So we're going to be safe in our lifetime. But yeah, another 5 billion years and our sun will be at this stage of its evolution. So yeah, it ranges a lot. Our star is going to be around for a long while, though. Good question. You want to pass?
Yeah. Like, is there only one black hole, or is there like many?
There's a lot of them out there, and it's not just the ones at the center. There's not just one in a galaxy. This is at the center of Pinwheel here. It's the biggest black hole in this galaxy, but there's a whole bunch of small ones too.
So in the middle of so in the galaxy there could be a lot of black holes, but the one in the middle of the galaxy is always the biggest one.
Yes, that is often the case. It's kind of the central point in the galaxy, at least spiral galaxies. Okay, do you want to pass the mic over there? Good question.
Well, will a black hole like get stuck in an orbit of another black hole?
Ooh, that's a really good question. And yes, that's how these ones form. So these big black holes at the center of galaxies form because black holes collide. And that mass can add. So just like anything, like a star is colliding, planets colliding, that mass collects over time. So yeah, exactly. I think I don't think we've witnessed it yet, but that's the math, yes. And it's also like some scientists think that the major events that we experience with gravitational waves, some of the origins of those, and that's why they're so interested in detecting more of them over time. It's a fairly new area in science, but that could be the origin for some of those gravitational waves, are black hole collisions. Yeah.
And also, like, why are some black holes big and some are small?
It just depends on the star that they came from. So something like that big star we talked about earlier, VY Canis Majoris, that one goes supernova. It leaves behind a big black hole. But a star smaller than it would leave behind a smaller black hole.
Also, would a bigger black hole suck up a smaller black hole?
I think it depends. It all depends on mass. Good question. So that's
also, what makes the ring of a black hole?
The ring of that's that disk. That's that disk of material that forms around it. From some of it is going to be from the star, but also some of it is going to be what's near the star or what it comes into contact with over time. let's give this the mic over there. Yep.
Shouldn't the star lose some gravitational pull after some time? Is because it turns smaller?
Certainly, like, again, depending on what state you're in the cycle, but if it loses mass, it definitely loses some gravity, because those are directly related. So for sure, yeah.
Then how does it get like so much gravitational pull?
Oh, you're
When
talking
it's a dying star.
the switch
black
over
holes.
from
A
star to
dying
black
star
hole.
to a black hole, yes.
Got you, yeah. That's where the density plays the role. So if you're thinking back to this slide here, you're talking about going from this huge, huge object in space that's very massive,
Yeah.
but very wide, to something that's much smaller, something Earth-sized even, going from a star to Earth-size, but keeping most of the mass. And when you keep most of that mass, you create this hyper-dense source of gravity. And that's what you see here. It just pulls space-time down, way, way down into what we know as a black hole. So it's how you compress all this matter into a singularity, a singular space.
But
Yeah,
shouldn't when the black hole dies release it, all of it, so it shouldn't leave any like dent in the like basically space time?
So you're thinking of, well, the black holes do, there is another phenomenon with black holes which they do radiate over time, and they do decay themselves, for sure, on like, I forget what the time scale is. It might even be trillions of years. It takes a long time, but they will lose mass over time, yes.
But like in the diagram it says like the space time's bending it. But when something explodes, doesn't that like turn into like basically nothing, only into a small atom?
I think the tricky part here when we talk about black holes is like what they actually look like and what they actually are. And the important thing here is you can kind of think of it as a hyperdense, like our white dwarfs are pretty dense. They end up being pretty strong sources of gravity. Neutron stars even more so, very dense, very small stars. But this black hole here is that stage after it. If it's massive enough, it becomes so hyperdense and so massive, or there's so much mass there in a small space, that nothing can escape it. So it becomes this almost like an inverted star in a way. Yes. Oh, we do. Okay, let's pass the mic over to the other side. Oh, that's perfect. Thank you. Yes. Yeah. Go ahead.
So Stevenson 2-18 is a really big star.
Ooh, what was it again?
Stevenson 2-18 is a really big star.
I'll have to look that one up. I don't know that one. That's cool.
But it will actually explode into a black hole.
Oh, it sounds it. If it's a big star, yeah. It'll become a black hole one day. Oh, cool. I'll look that one up. Thank you. We'll wrap up. You are a very inquisitive bunch, and I love it. That's amazing.
So we have a question here and then one more here. All right.
What makes the ring of a black hole glow and like a star cloud glow?
That is the type of material it's made up of. Just like likely where some of that came from was a star. It's being energized as it approaches the black hole. It's being spun around, and there's so much friction that material's rubbing together and creating energy. Just like when something is very, very hot, it has a glow to it. It starts emitting light. That's basically what's going on there with that material around it.
Also, why is it only like a disc? Like a very thin layer. Why can't it be like all spin around the black hole?
Yeah, when things spin in space, they flatten and spread out. Especially when it's like dusty and material like particles in space, it spreads out. That's good.
Why is it like some of the black hole pictures? Why is it like light sticking out the dark places of the black hole? Why is the light sticking out? Isn't the light supposed to be sucked in?
that's another level of radiation that happens with the poles. You are asking some great questions. If you have more, I'd be happy to answer some of these too afterwards. Let's do one more, and then we'll wrap up the stream, and we can talk more. Yes, yeah, this is open to anyone that wants to try it again. Yep.
Yeah, I also had a question about that singularity, like graphic. It's like everything is on one plane, so it describe like the gravity sucks everything down. But in the three-dimensional space, it's not like it's just everything goes towards the center of it. So I always got confused with those.
It's like the space-time curve.
Yeah.
Yeah, that's the space-time, that curvature, that model is being rendered in that 2D plane. Let's go back to it. Yeah. So you only have your x, y, z coordinates, but I think it depends on like how you're framing space. Like this particular model is framing gravity and how gravity behaves in space. So the 3D component to it is like the physical component is like how do objects react to this curve of gravity. And the way that would react is, in this model, is if something's out here, it's orbiting around safely. And then if something gets close enough, it will just collapse into the object. So it's like a projection, I guess, of how that gravity is behaving. It's the best way to think about it. Not perhaps not exactly how space itself is shaped around the object.
Jen, I'm just going to jump in for a second because I think there's a lot of questions here. And what I would encourage is folks to continue with you up front, but also try out the demonstration there for now. But it is getting late.
It is, yeah.
So I'm just going to have you wrap it up.
Okay,
this is,
perfect.
I mean, this is an amazing conversation, and it's a complex one.
Yeah,
but Janelle, I'm going to have you finish up. And then guys over here, I say we go up front and we explore the model and talk some more up front.
Yeah, we have posters and everything. Like
so
we've got
yeah.
lots of stuff for you. So yeah, thank you so much for everyone attending Black Holes on Black Friday. I hope the skies are still clear so we can go check out the telescopes, see Saturn and the moon. And then yeah, come check out the black hole. Those on the live stream, thanks for watching. We'll see you next week. Thanks everyone.